Write the common difference of an AP arithmetic progression whose nth term is given xn plus y. Given in an arithmetic progression AP, nth term is given an is equal to xn plus y. The common difference of an AP is given by an minus 1 for n is greater than 1. So we can write an is nothing but xn plus y minus an minus 1 is x times of n minus 1 plus y, that is xn plus y minus x times of n minus 1 minus y. We can simplify xn plus y minus xn minus of minus plus x minus y. So we can cancel here y and y, and xn gets cancelled, so I have only left with x. Therefore we can say common difference d is equal to x for the given AP. Write the common difference of an arithmetic progression, the sum of whose first n terms is given p by 2 n square plus qn. Given in an arithmetic progression AP, sum of first n terms Sn is equal to p by 2 n square plus qn, and then we can find sum of first one term, which is equal to a1 we can consider, which implies that s1 is equal to p by 2 into 1 square plus q times of 1, that is p by 2 plus q, and then sum of first two terms, which can be taken as a1 plus a2. So here we shall consider n is equal to 2, s2 is equal to p by 2 times of 2 square plus q times of 2, which is equal to p by 2 into 4 plus 2q, that is s2 is equal to 2p plus 2q, and then we have an is equal to sn minus 1, means nth term can be obtained by using the sum sn minus 1. So we can find the second term, which is equal to s2 minus s1, that is s2 is 2p plus 2q minus of s1 is p by 2 plus q. Upon simplifying, so we get 2p plus 2q minus p by 2 minus q. 2p minus p by 2 is 3p upon 2, and 2q minus q is plus q. So this is the second term. So we have the first term a1 is equal to p by 2 plus q, and the second term a2 is equal to 3p by 2 plus q. Then the common difference can be obtained. Common difference can be obtained from these two terms. D is equal to a2 minus a1. So which can be taken, D is equal to 3p upon 2 plus q minus a1 is p by 2 plus q, that is 3p upon 2 plus q minus p upon 2 and minus q. So we can cancel here q and q, and 3p minus p is nothing but 2p upon 2, which is equal to p. Therefore the common difference is p. If the sum of n terms of an AP arithmetic progression is 2n square plus 3n, then write its nth term. Given in an arithmetic progression AP, sum of first n terms Sn is equal to 2n square plus 3n, and we know that nth term can be obtained, nth term an can be obtained by using the sum as Sn minus 1. So we can find nth term an is equal to Sn is 2n square plus 3n minus Sn minus 1. We can use it as 2 times of n minus 1 whole square plus 3 times of n minus 1 by substituting in place of an n minus 1. In place of an n minus 1 we have to substitute, so we'll be getting this. So 2n square plus 3n minus, let us simplify this, 2 times of n minus 1 whole square, that is n square, minus 2n plus 1, and here plus 3n minus 3, or we can add 2n square plus 3n minus of 2n square minus 4n plus 2 plus 3n minus 3, and let us remove the brackets and write 2n square plus 3n minus 2n square, negative of negative plus 4n minus 2 and minus 3n and minus of minus plus 3. So we can cancel here 3n and 3n, and negative 2n square gets cancelled, and we have 4n minus 2 plus 3 is plus 1. So 4n plus 1 is the answer. That's the nth term. If log 2 power x minus 1 and log 2 power x plus 3 are in arithmetic progression AP, then write the value of x. Since we know that if a comma b and c, if a, b and c are in arithmetic progression, then we have 2 times of b is equal to a plus c. So here log 2 power x minus 1 and log 2 power x plus 3 are in arithmetic progression. So let us consider this is a, say this is b and c, so which implies here 2 times log 2 power x minus 1 is equal to log 2 plus log 2 power x plus 3, and by using the laws of logarithm we have m times log a is equal to log a power m, and we can say log a plus log b is equal to log ab, and logarithm to the same base, suppose the base is x here, logarithm to the same base, if they are equal then we can consider a is equal to b. So let us use these properties to solve this equation. So 2 times log of 2 power x minus 1 we can write log 2 power x minus 1 to the whole square is equal to, by using the first property, and the second log a plus log b property, so we can write log 2 times of 2 power x plus 3. So which implies since logarithm with the same base are equal, so we can write 2 power x minus 1 whole square is equal to 2 times of 2 power x plus 3. So that is 2 power x minus 1 whole square, we can write 2 power x whole square plus 1 square minus 2 into 2 power x into 1 is equal to 2 into 2 power x plus 2 into 3, which is 6. So we can write 2 power 2x, or let me write 2 power 2x, 2 power x whole square, and minus 2 into 2 power x, and again the term will come here minus 2 into 2 power x plus 1 minus 6 is equal to 0. So which implies 2 power x whole square minus, so here minus 2 into 2 power x into minus 2 into 2 power x, we can write 4 times 2 power x and minus 5 is equal to 0. So let us consider for some time 2 power x is equal to some p. So which implies p square minus 4 into p minus 5 is equal to 0. So let us factorize this. P square minus 4p minus 5. We can also write p square minus 5p plus p minus 5. We can take p common. P minus 5 plus 1 times of p minus 5. So we can write here p minus 5 into p plus 1. So this expression we can write equation p minus 5 into p plus 1 is equal to 0. So we can say here p minus 5 is equal to 0 or p plus 1 is equal to 0, which implies p is equal to 5 or p is equal to minus 1. So we can write here p is nothing but, let us consider back 2 power x. So 2 power x is equal to 5 or 2 power x is equal to minus 1. And since we know that conversion logarithm into, suppose log exponential form, log a to the base m is equal to b, which implies m to the power b is equal to a. This is logarithmic form to exponential form. So 2 power x is equal to 5. We can write it as log, the base is 2, log 5 to the base 2 is equal to x. And here we can write log the base is 2 and negative 1, which is equal to x. But this is not possible, because as per the condition, the log a to the base a must be positive, above 0. So this is not possible. Therefore we can consider x is equal to log 5 to the base 2. Okay. If the sums of n terms of two arithmetic progressions are in the ratio 2n plus 5 is to 3n plus 4, then write the ratio of their mth terms. Let us consider the two arithmetic progression. Let small a and small d be the first term and common difference of first arithmetic progression, and capital A and capital D be the first term and common difference of the second arithmetic progression. It's given that sum of the n terms of two arithmetic progressions are in the ratio 2n plus 5 is to 3n plus 4. So let us consider Sn be the first sum of first n terms of first AP, and Sn dash let us consider be the sum of first n terms of second AP. The ratio is given 2n plus 5 upon 3n plus 4. And so we can sum to n terms in arithmetic progression is n by 2 into 2a plus n minus 1 into d. So by using this formula, let us write n by 2 into 2 times a plus n minus 1 into small d upon n by 2. In the second progression we have capital A, so we can write 2 times capital A plus n minus 1 into capital D is equal to 2n plus 5 upon 3n plus 4. So further simplifying, we can cancel here n upon 2 and we can take 2 common and we can write a plus n minus 1 upon 2 times of d upon, again 2 common in the denominator, a plus n minus 1 upon 2 times of capital D, which is equal to 2n plus 5 upon 3n plus 4. So we can cancel here 2 and 2, and let us consider we need to find the ratio of their mth terms. We know that mth term is equal to a plus m minus 1 into d. It's a general term. So the ratio of their mth terms, let us write am and capital Am, which is equal to a plus m minus 1 into d upon capital A plus m minus 1 into capital D. So to find these values, let us compare a plus n minus 1 upon d upon 2 into d as a plus m minus 1 into d. So when comparing, so m minus 1 must be equal to n minus 1 upon 2. So that is 2 times m minus 1 is equal to n minus 1, or we can write 2m minus 2 is equal to n minus 1, or we can write this as 2m minus 2 plus 1 is equal to n. So that is 2m minus 1 is equal to n. It's to get the mth terms ratio, so we need to consider n as 2m minus 1. So let us consider 2m minus 1 as n, or by substituting n is equal to, put n is equal to 2m minus 1. So in equation 1, so that we will get the numerator will be a plus m minus 1 into d, you will get, and denominator capital A plus m minus 1 into capital D, which is equal to, let us substitute here, 2 times of 2m minus 1 plus 5 upon 3 times of 2m minus 1 plus 4, which is equal to 4m minus 2 plus 5 upon 6m minus 3 plus 4. So which is 4m, 5 minus 2, that is 3 upon 6m, 4 minus 3, which is 1. So we can say that the ratio of mth terms is 4m minus 4m plus 3 upon 6m plus 1. And this can also be obtained by using this simple formula. If the ratio of the sums of n terms of two APs is given, then the ratio of their nth terms is obtained by replacing n by 2n minus 1. So here we replaced n as a 2m minus 1. Similarly, for any problem, if sum of n terms of two APs is given, then we can find the ratios by replacing n as 2n minus 1. Okay. Write the sum of first n odd natural numbers. Odd natural numbers are 1, 3, 5, 7, 9, and so on. Nth odd natural number will be 2n minus 1. Since these are in arithmetic progression, AP, whose first term a is equal to 1 and common difference is 2, and let Sn denotes the sum. Let Sn denotes their sum. So we have Sn is equal to 1 plus 3 plus 5 plus and so on 2n minus 1. And since we know sum to n terms in AP is Sn is equal to n by 2, 2a plus n minus 1 into d, or we can write Sn is equal to n by 2 times of a plus the last term l. So here the last term l is equal to 2n minus 1 and first term a is equal to 1. So let us write, so Sn is equal to n by 2 into a plus means first term plus last term, that is 2n minus 1. On simplifying, n by 2 times 1 plus 2n minus 1, so plus 1 minus 1 gets cancelled, so this is n upon 2 into 2n, so we can cancel 2 and 2 and we can write n square. Therefore we can conclude that the sum of first n odd natural numbers is sum of first n odd natural numbers which is equal to n square. Okay. Write the sum of first n even natural numbers. Even natural numbers are 2, 4, 6, 8, 10 and so on. Last nth even natural number is 2n. So which is the sequence is an arithmetic progression whose first term is 2 and common difference d is equal to 2, and their sum let us denote Sn is equal to 2 plus 4 plus 6 plus 8 plus and so on up to 2n. Since we know that in an arithmetic progression sum of first n terms is n upon 2, 2a plus n minus 1 into d, or we can also write n upon 2 times of a plus l. L is the last term. So here first term a is equal to 2 and the last term is 2n. So let us substitute, which is equal to n upon 2, first term is 2 plus the last term is 2n, or we can take 2 common, 1 plus n, or here we can cancel 2 and 2 and we can write n into n plus 1. Therefore we can say that sum of first n even natural numbers is equal to n into n plus 1. Okay. Write the value of n for which nth terms of the two A.P.s 3, 10, 17 and so on and 63, 65, 67 and so on are equal. So given two arithmetic progressions, first one 3, 10, 17 and so on. So let us consider a be the first term and d be the common difference. First term and common difference respectively. And the given second one, the second sequence is 63, 65, 67 and so on. Let us consider here capital A and capital D be the first term and common difference respectively. So we have A is equal to 3 and D is equal to 10 minus 3, which is equal to 7 and general term in the first term, first sequence, let us consider an is equal to a plus n minus 1 into d, that is 3 plus n minus 1 into common difference is 7. So this can also be written 3 plus 7n minus 7, or we can write 7n, 3 minus 7 is minus 4. And in the second sequence, capital A is equal to 63 and capital D is equal to 65 minus 63, which is equal to 2, and the nth term, let us take capital AN is equal to A plus n minus 1 into capital D, which is equal to 63 plus n minus 1 into capital D is 2. So we can write 63 plus 2n minus 2. So that is 61 plus 2n. So the two nth terms are mentioned here, and now we need to find the value of n for which the nth terms of two A.P.s are equal. So given that nth term in the first A.P, that is an, is equal to nth term in the second sequence, that is capital En. So we can write 7n minus 4 is equal to 61 plus 2n. So let's take this in equation 1 and this is 2. So from 1 and 2 we can mention. So we can write 7n minus 2n is equal to 61 plus 4, that is 5 times n is equal to 65. So which implies n is equal to 65 upon 5, that is 13. So the value of n is 13, for which nth terms of 13th terms of 2 APs are equal. Okay. If 3 plus 5 plus 7 plus and so on up to n terms upon 5 plus 8 plus 11 plus and so on up to 10 terms is equal to 7, then find the value of n. So here given the ratio of two series, the numerator 3 plus 5 plus 7 plus and so on up to n terms, this series is, which is an arithmetic progression whose first term a is equal to 3 and common difference d is equal to 5 minus 3, that is 2, and hence sum to n terms we can write Sn is equal to n upon 2 2a plus n minus 1 into d, that is n upon 2 2 times of 3 2 times of 3 plus n minus 1 into d value is 2. So which is equal to n upon 2 into 2 times 2 taken common 3 plus n minus 1. So we have n times of 3 plus n minus 1, that is 3 minus 1 is 2. So n into n plus 2 is the sum to n terms of the given numerator series. And now let us consider the denominator. Consider denominator, that is 5 plus 8 plus 11 plus and so on up to 10 terms. So given series is also an, which is also an AP arithmetic progression whose first term let us consider capital A is equal to 5 and the common difference let us take capital D is equal to 8 minus 5, that is 3, and sum to n terms, let me take s dash of n is equal to, so we have n by 2 times of 2a plus n minus 1 into n minus 1 into capital D. So we can write here n upon 2, here 10 terms are there, so here n is equal to 10. So 10 upon 2 times of 2 times of 5 plus n minus 1, that is 10 minus 1 times of d is 3. So upon simplifying 2 5 times, so 5 times 2 5s are 10 plus 10 minus 1 9, 9 3s are 27. So we have 5 times 27 plus 10 37. So here 35 is a 150 plus 35 185 is the sum, the denominator. So given that the numerator upon denominator is equal to 7, given that, so let's consider this as 1 and 2, n into n plus 2 upon 185 is equal to, the ratio is given 7, which is equal to 7, or we can write n into n plus 2 is equal to 7 into 185, or 185 7 times. Instead of this we can write 185 factorization, 5 3s are 15, 5 7s are 35. So we can write here 7 into 5 into 37, or we can write 7 5s are 35 into 37 we can write it as 35 plus 2. And then comparing on both the sides, n into n plus 2. So we can say very clearly that n is equal to 35. So we can consider that, which is possible, n is equal to 35. The sum of 3 plus 5 and so on up to 35 terms upon 5 plus 8 plus and so on up to 10 terms, the ratio will be equal to 7. Okay. If mth term of an AP is n and nth term is m, then write its pth term. In an AP, general term an is given by a plus n minus 1 into d, where a is the first term and d is the common difference. And it's given that mth term, that is am, is equal to n, that is a plus m minus 1 into d is equal to n. Let us consider this in equation 1. And also given nth term is m, that is an is equal to m. So we can write a plus n minus 1 into d is equal to m. Let us consider in equation 2. So solving 1 and 2, or subtracting 1 and 2, equation 1 minus equation 2, which implies a plus m minus 1 times of d is equal to n, a plus n minus 1 times of d is equal to m. Subtracting both, a and a gets cancelled, and here m minus 1 minus of n minus 1 times of d is the common, and which is equal to n minus m. On simplifying, m minus 1 minus n plus 1 times of d is equal to n minus m. So here minus 1 plus 1 gets cancelled. So m minus n times of d is equal to, we can write minus of m minus n, or we can write d is equal to minus of m minus n upon m minus n. So the common difference is minus 1. So we got common difference value minus 1. Let us substitute. Put d is equal to minus 1 in any one of the equation. Let us take equation 2 into, so we can write a plus n minus 1 into d value, that is minus 1, is equal to m, or we can write a minus n plus 1 is equal to m. So which implies a is equal to m plus n minus 1. So we got the first term, a is equal to m plus n minus 1. And now we need to find the pth term. So let us consider AP, which is equal to a plus p minus 1 into d. First term a is equal to m plus n minus 1 plus p minus 1 into common difference is minus 1. So on simplifying, m plus n minus 1 and p of minus 1 is minus p, and minus of minus plus 1. So we can cancel here and we can give the answer m plus n minus p. Therefore pth term is nothing but m plus n minus p. Okay. If the sums of n terms of two APs are in the ratio 3n plus 2 is to 2n plus 3, then find the ratio of their 12th terms. Given the sums of n terms of two APs are two arithmetic progressions are given, whose sums of n terms are in the ratio 3n plus 2 is to 2n plus 3. Let us consider Sn upon Sn dash is equal to 3n plus 2 upon 2n plus 3, and we need to find the ratio of the 12th terms. Let us consider A12, divided by capital A12 are the terms. So we need to find this. And since we have a property, if the ratio of the sums of n terms of two APs is given, then the ratio of their nth terms is obtained by replacing n by 2n minus 1. So replacing n by 2n minus 1 means here n is equal to 12 we can use, and we have to replace here in place of n we have to write 2 times of 12 minus 1, that is replace n by 2 times of 12, that is 24 minus 1, 33. So replace n by 23 in the sum to get the ratio of the 12th terms. So therefore A12 upon A12 is equal to 3 times of 23 plus 2 upon 2 times of 23 plus 3, which is equal to, so 23 3 times 69, 69 plus 2 upon 23 2 times 46 plus 3, so we have 71 upon 49. So therefore the required ratio is equal to 71 is to 49. Okay. If the fifth term of a GP is 2, then write the product of its 9 terms. Given that in a GP, fifth term is equal to 2. So in general term of GPs, it's a general term, nth term is given a into r to the power of n minus 1, where a is the first term and r is the common ratio. So we can write a5 as a into r to the power 5 minus 1, that is 4. A r power 4 is equal to 2. This is given. And we need to find the product of 9 terms. So product of 9 terms is equal to, so if a is the first term, our first 9 terms product, a into ar into ar square into ar power 3 into, and so on. 9th term will be ar power 9 minus 1, that is 8. So which is equal to a into a into a into and so on, 8 9 times, and again r to the power 1 into r to the power 2 into r to the power 3, r power 3 into r power 4 into and so on, r power 8. So here a is multiplied 9 times, so we can add a to the power 9 into r to the power, since we know that a power m into a power n is a power m plus n, so we can add r power 1 into r power 2 and so on, r power 8 is equal to r to the power, the sum of the numbers 1 plus 2 plus 3 plus and so on up to 8, which is equal to a to the power 9 into r to the power, we know that sum of first n natural numbers 1 plus 2 plus 3 and so on up to n is equal to n into n plus 1 by 2, sum of first n natural numbers. So we can write here, so r to the power, here 8 natural numbers are there, sum of 8 natural numbers is 8 into 8 plus 1 by 2, that is a to the power 9 into r to the power 8 into r2, we can cancel here 2 4 times, so 4 into 8 plus 1 is 9. So this can also be written a into r to the power 4 whole to the power 9, and we know that the fifth term is ar power 4, so ar power 4 is given 2, so we can write here ar power 4 is 2 to the power 9, so 2 power 9 value is 512. So therefore we can conclude that the product of first 9 terms in GP whose fifth term is given 2 is 2 power 9, that is 512 is the answer. If p plus q term and p minus q terms of a GP are m and n respectively, then write its p term in a GP. The general term is given by an is equal to a into r to the power n minus 1, where a is the first term and r is the common ratio. So let us consider a the first term and r is a common ratio. Then p plus q term we can write it as a p plus q is equal to a into r to the power, we can write r to the power p plus q minus 1, and also given p minus q term, that is a p minus q is equal to a into r to the power p minus q minus 1, and these terms of a GP are respectively m and n, so which is equal to m and here say n. Make this an equation 1 and 2. So let's multiply 1 and 2. Multiply 1 and 2. So we'll have a into r to the power p plus q minus 1 into a into r to the power p minus q minus 1 is equal to m into n, or we can write this as a into a square into r to the power p plus q minus 1 plus p minus q minus 1, so is equal to m into n. So we can cancel, so plus q and minus q, and again p plus q, that is 2 a square into r to the power 2p minus 2, which is equal to m into n, that is a square into r to the power 2 times of p minus 1 is equal to mn, or we can write a into r to the power p minus 1 whole to the power 2 is equal to mn, or this can also be written a into r to the power p minus 1 is equal to root of mn, and we know that a into r power n minus 1 is nth term, so we can write this is pth term, so ap is equal to root of mn, that is a pth term. So pth term of GP is square root of mn is the answer. If log a to the base x, comma a to the power x by 2 and log x to the base b are in geometric progression GP, then write the value of x. We know that if a comma b and c are in geometric progression, then we have b square is equal to a into c. So here let us consider a is equal to log x to the base a and b is equal to a to the power x by 2 and c is equal to log x to the base b. Then as per the rule, since they are in geometric progression, we can write b square, that is a power x by 2 whole square is equal to a into c, that is log a to the base x into log x to the base b. So on simplifying, a to the power of x by 2 whole square is a power x is equal to, and we know that by using the property log m to the base a into log a to the base n is equal to log m to the base n. So here log a to the base x into log x to the base b can be written as log a to the base b. And also converting logarithmic form to exponential form, if a power m is equal to n, then this can be written log n to the base a is equal to m. So we can write a to the power x is equal to log a to the base b, so which implies that log of log a to the base b, and the base is here a, is equal to x. So we can say that therefore x is equal to log of log a to the base b, and here the base is a. This is the answer. Okay. If the sum of an infinite decreasing GP geometric progression is given 3 and the sum of the squares of its terms is 9/2, then write its first term and common ratio. Let a be the first term, and r be the common ratio. R be the common ratio, and it's an infinite decreasing GP, so consider to be mod r is less than 1, that is r lies between -1 to +1. Then sum to infinity s infinity we can write a plus ar square and so on up to infinity. So by the sum to infinity formula we can write a upon 1 minus r, where mod r is less than 1 and a is the first term. Let's consider in equation 1, and sum of the squares of the terms, sum of the squares of the terms can be taken as a square plus ar whole square plus ar square whole square plus and so on up to infinity, which is equal to, the sum is given 9/2, that is a square plus a square r square plus a square r power 4 and so on up to infinity, which is equal to 9/2. We can say that the left side series is also an GP, so that's an infinite GP. And since mod r is less than 1, that is r lies between -1 to +1, so which implies r square must be lies between 0 and 1. So we can consider to be 0 to 1, and so we can say it is also sum to infinity, and the first term is a square. So sum to infinity of the squares can be taken as a upon, that is a square upon 1 minus r square is a common ratio. So here the first term is a square and common ratio is r square, and sum to infinity we can apply since r square is mod of r square is less than 1, that is 0 to 1 we can consider, and s infinity we can, and this is equal to 9/2 given. So we have a square upon 1 minus r square is equal to 9/2, which on simplifying, so we can write a upon 1 minus r into a upon 1 plus r is equal to 9/2, and since we have a upon 1 minus r, sum of an infinite GP decreasing GP is given 3, so which is given as a 3. So from the first one, since a upon 1 minus r is equal to 3, so let us substitute here 3 times of a upon 1 plus r is equal to 9/2, or we can write a upon 1 plus r is equal to, so here 9/2 into 3, so which is equal to again 3/2 we can write. And again, so cross multiplying, a is equal to 3/2 times of 1 plus r, and from here we can write a is equal to 3 times of 1 minus r, so we can substitute from, say this is second and this is third, from 2 and 3, we can write 3 times of 1 minus r is equal to 3 times of 1 minus r is equal to 3 upon 2 times of 1 plus r, or simplifying here 3 gets cancelled. So 2 times of 1 minus r is equal to 1 plus r, or we can write 2 minus 2r is equal to 1 plus r, or 2 minus 1 is equal to r plus 2r, that is 3r. So we can get r is equal to 1 by 3. Substituting r is equal to 1 by 3, or put r is equal to 1 by 3 in equation, say equation 2, so which implies that a is equal to 3 times of 1 minus r, that is 1 by 3, which is equal to 3 times of 3 ones are 3, 3 minus 1, that is 2 upon 3, which is equal to 2. Therefore we can say the first term is 2 and the common ratio is 1 upon 3. If pth term, qth term and rth terms of a GP are given x comma y comma z respectively, then write the value of x power q minus r into y power r minus p into z to the power p minus q. Since we know that in GP, general term an is equal to a into r to the power n minus 1, let us consider, let a be the first term and capital R be the common ratio. So we can write a into r to the power n minus 1 is the general term. So therefore we can write pth term, that is AP is equal to a into r to the power p minus 1, which is given x, make this as 1, and qth term aq is equal to a into capital R to the power q minus 1, which is equal to y, say this is second equation, and third one rth term is given ar is equal to a into r to the power r minus 1, which is equal to z. Take this as an equation 3. Then we need to find x power q minus r into y to the power r minus p into z to the power p minus q. So let us consider x to the power q minus r into y to the power r minus p into z to the power p minus q, which is equal to x to the power q upon x to the power r into y to the power r divided by y to the power p into z to the power p divided by z to the power q. So from 1, 2 and 3, x is nothing but a into r to the power p minus 1 whole power q upon, here x is nothing but again same a into r to the power r minus 1 whole to the power r into y is nothing but a into r to the power q minus 1 whole to the power r divided by a into r to the power q minus 1 and whole to the power p into z is nothing but a into r to the power r minus 1 whole power p divided by a into r to the power r minus 1 whole to the power, again we can write it's a cube. So upon simplifying, we can write this as a power q into capital R to the power pq minus q upon a to the power r into capital R to the power r square minus r, again into a to the power r into r to the power of capital R to the power qr minus r divided by a to the power p into r to the power pq minus p into a to the power p into capital R to the power rp minus p upon a to the power q into capital R to the power rq minus q. So here we can cancel the terms. A power q and A power q gets cancelled, A power p gets cancelled, and A power r and A power r gets cancelled, and remaining terms we can write here. Sorry, this is a small correction. Here it is p. Say this is p here, p minus 1. So we can write here p. So we can write here pr minus r. And so we can write here r to the power pq upon r to the power q, and again here r to the power pr into r to the power r into r to the power qr upon r to the power r into r to the power of r to the power pq into r to the power p into r to the power rp upon r to the power p, and again r to the power rq into r to the power q. So we can cancel the terms r power pq, r power pq, and r power r, r power r, r power qr, and r power qr, and r power rp, r power rp, r power q, and r power p, and r power p. Everything gets cancelled, so answer is 1. So we can conclude that finally the answer is 1. If a1, a2 be two arithmetic means and g1, g2 be two geometric means between a and b, then find the value of a1 plus a2 upon g1 into g2. We know that if there are n arithmetic means between a and b, then the sum of n arithmetic means is equal to n times arithmetic mean of the first and last number, that is a and b, that is n times of a plus b by 2. So here in this problem there are two arithmetic means, therefore their sum is equal to sum of two arithmetic means is equal to a1 plus a2, which is equal to n times means two arithmetic means, so 2 times arithmetic mean of the two numbers which are first and last, that is ab. So we can write a plus b by 2. So we can write a1 plus a2 is equal to a plus b. Similarly, and we know that if there are n geometric means between a and b, between two given numbers a and b, then the product of n geometric means is equal to, so we can write nth power of geometric mean of first and last number, that is a and b. Geometric mean of a and b to the power n, that is root of ab whole to the power n. So here there are two geometric means g1 and g2 between a and b. So we can write the product of two geometric means is equal to g1 into g2 is equal to root of ab whole to the power, here two geometric means, so we can take n is equal to 2. So root of ab whole square is ab. Therefore a1 plus a2 upon a1 plus a2 upon g1 g2 is equal to a1 plus a2 is a plus b upon g1 g2 is ab. So a plus b upon ab is the answer. If second, third and sixth terms of an arithmetic progression AP are consecutive terms of a geometric progression GP, then write the common ratio of the geometric progression. Let us consider small a and small d be the first term and common difference of an AP, so that we have the general term an is equal to a plus n minus 1 into d. So the second term we can write a2 is equal to a plus 2 minus 1 into d, that is a plus d, and third term we can write a plus 3 minus 1 into d, that is a plus 2d, and sixth term we can write a plus 6 minus 1 into d, that is a plus 5d, and this second term, third term and sixth term are in GP. So let R be the common ratio. Let us consider R be the common ratio of GP. Then we have the terms A2, A3, A6 of an AP are consecutive terms of GP, are consecutive terms in GP, that is a plus d, a plus 2d, a plus 5d are in geometric progression. And here R is a common ratio. We know that if A comma B comma C are in geometric progression, then the common ratio R is equal to B upon A, or we can consider C upon B. So let us consider the ratio, common ratio. Common ratio R is equal to, so we can take the ratios A plus 2D upon A plus D, and which will be equal to A plus 5D upon A plus 2D, since they are consecutive terms. So let us consider the ratio. Let's consider the two ratios. A plus 2D A plus 2D upon A plus D is equal to A plus 5D upon A plus 2D. And let us apply the component and dividend property. Component or dividendo. The property says if A by B is equal to C by D, then A plus B upon A minus B is equal to C plus D upon C minus B. The ratios will be equal. So let us apply the same here. Numerator A plus 2D plus of A plus D upon A plus 2D minus of A plus D is equal to A plus 5D plus A plus 2D upon A plus 5D minus of A minus A plus 2D. And simplifying, you will get A plus A, that is 2A, plus 2D plus 1D, that is 3D, upon, and here A minus A gets cancelled, 2D minus D, which is D, is equal to, here you will get 2A plus 5D plus 2D, 7D, upon, here A gets cancelled, 5D minus 2D is 3D. So let's consider to be D not equal to 0, so that we can cancel this D on both the sides, and cross multiplying 3 times 2A plus 3D is equal to 2A plus 7D, which implies 6A plus 9D is equal to 2A plus 7D. or 6a minus 2a, that is 4a, is equal to 70 minus 90, that is minus 2d. Or we can write a is equal to, or we can write d is equal to, let us write d. So d is equal to minus 4a upon 2, which is negative 2a. So minus 2a is a common difference. Let us substitute, put d is equal to minus 2a. In the equation, let us consider this to be 1. Say this is 1. So we can get r is equal to a plus 2d, that is a plus 2 times of d value is minus 2a upon a plus d, that is a plus of minus 2a, which is equal to a minus 4a upon a minus 2a, that is minus 3a upon minus a. So on cancellation you will get 3. Therefore we can say that the common ratio r is equal to 3. Okay, and here also we can observe, if suppose d is equal to 0, the common difference is same, then you will be getting the terms, all terms are equal, and the common ratio also will be equal. R is equal to 1, you may get it. If d is equal to 0, then common ratio may get 1. So here we avoided that d cannot be 0, so we got the answer r is equal to 3. Okay, write the quadratic equation, the arithmetic and geometric means of whose roots are capital A and capital G respectively. Let us consider alpha and beta be the roots of quadratic equation so that it's given A is arithmetic mean of capital A is given arithmetic mean of the roots alpha and beta, which is equal to, we can say the mean of alpha and beta is alpha plus beta by 2, and then capital G is given geometric mean of alpha and beta. So geometric mean of alpha and beta, we can take it as a root of alpha beta. So we have alpha plus beta by 2 is equal to A, that is alpha plus beta is equal to 2a, and also given geometric mean root of alpha beta is equal to g, or we can add alpha beta is equal to g square. And a quadratic equation when the roots are alpha and beta is quadratic equation when the roots alpha and beta has x square minus sum of the roots alpha plus beta of x plus alpha beta is equal to 0. So here alpha plus beta is 2 times a, say this is 1 and this is 2, so we can write x square minus of 2a of x plus alpha beta is g square is equal to 0 from 1 and 2. So we can write x square minus 2ax plus g square is equal to 0 is a required equation. Write the product of n geometric means between two numbers a and b. Let us consider n geometric means b g1, g2, g3 and so on, gn so that A comma G1 comma G2 comma G3 and so on Gn comma B are in geometric progression Gp, and we know that product of n geometric means between A and B is given by geometric mean of, or nth power of, we can say nth power of geometric mean of the two numbers A and B, that is G1 into G2 into G3 and 2 and so on Gn is equal to geometric mean of A and B is root of AB whole to the power n, or we can add AB whole to the power 1 by 2 whole to the power n, that is AB to the power of AB whole to the power of n by 2. So the product of n geometric means we can take it as AB whole power n by 2. If A is equal to 1 plus B square plus B cube and so on to up to infinity, then write B in terms of A given that mod B is less than 1. So here given A is equal to 1 plus B square plus B power 3 and so on up to infinity, and clearly we can say that this series is geometric series, which is an infinite geometric series. Its common ratio R is equal to B, and where mod B is less than 1, since we know that geometric series A plus AR square and so on up to infinity and so on up to infinity, we can say that A upon 1 minus R when mod R is less than 1. This is the formula we have for geometric series, infinite series, where mod R is less than 1. So here mod B is less than 1, which is common ratio. So therefore we can say that A is equal to, we can apply the formula, the first term A is equal to 1 upon R is equal to B, so that is 1 by 1 minus B, or by simplifying 1 minus B is equal to 1 upon A, or we can add 1 minus 1 upon A is equal to B, or we can add A minus 1 upon A is equal to B. Therefore B in terms of A is nothing but A minus 1 upon A. This is the answer.